Okay, so to start this kind of last topic on combinations, I want to present two scenarios to you. They're honestly the exact same sort of thing. Here's the first one, but with a slight difference. There's 8 teams in a tournament, and we're going to give medals to the top 3 teams. So, like I was saying yesterday, sometimes there's scenarios where there's winners and losers, right? How many people are going to get a medal? Well, 3 will get a medal, right? How many will not get a medal? 5, right? So one way that you could write this, if you wanted to, would be to say this. You could say, well, 8 people could finish first. They could, right? 8 could finish first. And then there could be then 7 people who could finish second. And there could be 6 who finish third. And then the remaining 5, sorry, nothing for you, right? Now, what we've been learning over the last little while is let's shorten this up a little bit. You could call this 8 factorial over 5 factorial, where the 8 on the top is the total number of people who are applying. The 5 on the bottom is the people who don't make it. Another way we learned we could write that would be 8 factorial over 8 minus 3 factorial, because really, isn't 8 minus 3 that same 5? This was known as basically 8 pick 3. That's like the fastest way of going. 8 people, we want 3 of you. Right. And I gave this scenario kind of silly yesterday in class, the idea of, well, what happens if there were 8 of us here, and I offered 3 prizes? I offered $1 million, a handshake, and a pen. Does order matter? Absolutely, I want the $1 million, right? If I offer $1 million, a handshake, and a pen, and I say the first person gets the $1 million, I want to be first, right? Order matters, right? But what happens if I give you a scenario where, what if everybody who wins, they all get the same thing? So what happens if I was offering $1 million to all 3 people who won? Do you really care whether you're the first one to get the million or the third to get the million? No, because now the prizes are the same. That's the scenario I have right here. Let's say there's 8 teams going to the district basketball tournament, and the top 3 get to go to provincials. Now, I don't care whether you finish first, second, or third, so long as you're in the top 3, you get to move on. Well, now do you really care? Well, maybe for pride, you want to be first, right? But if all that matters is that you move on, you finish top 3, well, then order really doesn't matter. What I'm going to show you today is that there's another way of writing that, known as 8 choose 3, where this is called a combination. You get what I'm saying here? So there are certain times in life where it matters what order things are in. And there are other times in life where it really doesn't matter at all, right? I gave this example earlier, your phone numbers. If I told you that there are 10 digits on the phone and I need you to type in 8 of them to make a phone number, 7 of them to make a phone number, and so you type in 1, 2, 3, 4, 5, 6, 7, that's not the same thing as you typing in 7, 3, 2, 1, 4, 3, 6. Right? Like order matters when you type in your telephone number. Right? For those of you who started doing the question about going to the Sunday bar, though, when you go to get toppings on your ice cream, does it really matter whether you get peanuts and then chocolate sauce or chocolate sauce and then peanuts? Does it really make a difference? I mean, except maybe to like really, really picky people, like it's the same thing, isn't it? So the issue then is you can't double count things, which I want to show you on this slide right here. If you can just fast forward for a second. Okay. Let's in this scenario here, this is basically you being dealt some cards of like hearts, clubs, diamonds, and spades. Okay. And let's say that I wanted you to be dealt 2 cards. Okay. Well, here's what could happen. You could be dealt the heart first, then the diamond, the heart, the spade, the heart, the club, the spade, the club, the spade, the diamond, the spade, the heart. But hey, I crossed this one out though. Hopefully you can see why. Here you have a spade and a heart, but hang on, we already counted a heart-spade combo right here. And if we really don't care which one you have in your hand first, then we can't double count something. You know what I'm saying here? Combinations are always smaller than permutations because in combinations we're not double counting the scenario that's already been had where you're just flipping the order around a little bit. So this is why like the only thing new as of this point is you haven't done the diamond club combo, but like a diamond with a heart, we had one of those over here. A club with the diamond, we already had one of those over somewhere else, right? So, do I have another slide showing this? No, I don't. Okay, so let me go back to this example right here and try to explain how this works. Do you guys recall the formula from way back when? It was N over A, B, C, something like that. Sometimes the best way of approaching this then is to break things up again into like winners and losers. And I want to do the previous example one more time here. This one right here, what you really have is you have a gold medalist. You have someone who's going to win silver. You have someone who's going to win bronze, and then you have 5 losers. Does that make sense? That's what happens here where order matters. You have a gold, you have a silver, you have a bronze, you have 5 losers. Well, one way of writing this would then be to say that you have 8 characters total. You have a single gold. You have a single silver. I don't even know why I'm writing these. That's pointless, right? But the one that you have 5 of are the five people who lose. Well, isn't that what I just wrote down here? But what if the scenario changes where there's not a first, a second, and a third, and then everybody else? But what if it's really either you're on the team or you're off the team? Tryouts, I think, are a really good example. Like when I think of you trying out for like rugby. It's like at the end of the day, I don't care whether they selected your name first or last. You're either on the team or you're off the team, right? So if you approach this one right here, in a way, 3 teams are winners, right? There's no distinction between the 3 winners. They're all in or they're all out. And there's 5 losers. Well, how do we write that using that same notation? Well, again, there's 8 teams out there. There are, rather than it being like a 1, and a 1, like it was in the previous example, which I don't bother writing though, all of the winners are indistinguishable from each other. So it actually means that there's a 3 and a 5. Okay, now I'm sorry that I'm a little all over the place, but the top one here is 8 over 5, and the bottom one is 8 over 3, 5. I want to make sure everyone's clear on that. Let me do one more color just to make sure that I'm not messing you up here. This one is 8 over 5. And then if I really wanted to, I could write in the 1s, because there's a gold, a silver, and a bronze that are all different. But the 5 people who don't make it, who cares? They all look the same. Whereas here, it's 8 over 3, 5. What's the difference between these two? Well, this one still has an 8. This one still has an 8, right? This one you divide by the 5. This one you divide by the 5. Now, this one here, when you divide by 1, it doesn't do anything. But what happens here when you divide by 3 factorial? It makes it smaller, this is what explains why permutations are always bigger than combinations. Okay? And so here's the notation we use to describe this. And there's a couple of different ones here. The first one is the easiest one. It's just NCR. Okay? If there's 8 people and we want to choose 3 of them, choose just means I don't care what order you go in. You're on the team or you're not. Okay? You might also see it written in this format here, a bracket and then 2 numbers on top of each other. For example, 8, 3 means the same thing as 8, choose 3. It's just another notation you might come across. Well, this is the exact same thing as there's 8 people. Now, n minus 3, that would be like 8 minus 3. That means 5 of you don't make it. 3 of you do make it. The 2 numbers on the bottom always have to add up to the top. Right? They have to. The reason why they don't in the previous example, in the other example, the 8 over 5 example, is that it doesn't look like they add up to the top, but they really did. It's just we didn't bother writing all of the 1s that are there. You get the idea here? So one last thing you need to know here. N always has to be bigger than R, which this kind of makes sense. I can't have 12 people and pick 100 of them to win. Right? I can have 100 people and pick 12 of them to win, but I can't pick more than I begin with. That's just a general sense rule. So once you see these twists here, then we can speed up some question types. So I'm going to try to plow through these a little bit faster than maybe before. You got 5 kids going on a class trip out of 10. How many ways can you select them? 10 choose 5. That's it, yeah. Does it matter who's the first one selected? Like, just imagine a scenario. A teacher comes into the room and says, okay, I need 3 of you. We're going right now. You, and you. I pointed to you first, but do you get anything special because you were first? Not really, right? So in a way, we have 5 winners, and we have 5 losers out of the 10, right? If you really want to kind of look at this here, there's 5 people who win the trip, 5 who lose. So it's really 10 total numbers over 5 and 5. Well, that's what this notation right here is the shorter way of doing. That's all. So let's do the exact same thing here. There's 15 employees. 3 get to go give a presentation while 12 are left behind. How could you do this then? Yeah, 15, choose 3 of them. If you guys have your calculators, by the way, can someone find me what 15 choose 3 is as a number? I normally skip that, but I want to make a point on this one here. 455? So I want you to change your perspective here. This is a presentation, and you're excited to go because you're presenting to Wayne Gretzky. Now that's a once-in-an-opportunity, and like you're excited to go. So there's 15 of you, and I'm sorry, only 3 of you have to go. And so when you look at it from the perspective of I want to go, there's 3 of you, right? But what if it's like the world's worst presentation, and you don't want to go, and they're asking like, who wants to go, and everyone's kind of like, don't look at me. You get what I'm saying here? Well, in that way, wouldn't it be just as good to say, well, there's 15 people, and 12 of you don't have to go, right? I'm going to choose 12 people who don't have to go. Please don't make it me, right? Try this in your calculator. What's 15 choose 12? It's the same thing. Because really, when you look at it, in this example right here, I won't write them all out, but essentially you had a whole bunch of winners, right? And you had a whole bunch of, and you had 3 losers, right? So the way you'd write it is 15 over the 3 who win and the 12 who lose. But isn't that the exact same thing as changing your perspective and saying, "Oh, please don't send me, send those guys"? Isn't does the order of the numbers on the bottom, does it really matter which one goes first, the 13 or the 12? Well, no. So you could look at it from the perspective of there's 15 people, 3 of you get to go. Or you could look at it from the perspective of there's 15 of you and 12 of you don't have to go. Right? Like when it comes to not caring about order, both sides are kind of the same. Right? So long story short, I can show you a couple other little tricks here. Like for example, if I gave you 700, choose 13, this is going to be the exact same number as 700, choose what? Good. Those two things should be the same as each other. Right? Here, 13 of you get to go. Here, 687 of you don't have to go. Right? Same concept. So it's kind of a unique thing on how the formulas work for choose. So, okay, I need to show you this just so that you've learned lottery math at one point in your life. You guys heard of the Lotto 649 at some point, right? The way 649 works is that there are 6 numbers selected out of 49 total. So like back in the day, they used to have like the Lotto girl who, would probably, stand up there. They'd have like a little tub of balls. Maybe they still even do this. I don't know, right? They press the button. One ball shoots up. She holds it up. 11. Puts in a little thing there. You know what I'm talking about here? That sort of thing, right? And so what they'd do is they'd have 49 balls in a tub, and they'd pick out 6 of them. Well, at the end of the day, when you select your numbers, any of you guys ever watched Lost? Okay, so let's say if you know Lost, you pick the numbers 4, 8, 15, 16, 23, 42. Those are the special numbers on Lost. Let's say you pick those numbers. I don't care what order they're selected in. If you have the numbers that they select, you win the lottery. So essentially, the way that the Lotto 649 works is that there's 49 numbers, and you need to choose 6 out of them. If you get your 6 numbers to match their randomly selected 6 numbers, you win the lottery. Right? So I need you guys to do me a favor here. Grab a calculator and tell me how many different ways could those 49 balls be selected for 6 of them. If I don't care what order they go in. Like if I pick 1, 2, 3, and they come in 2, 3, 1, it's the same thing. What's the number? Just read it out to me. 1, 3, 9. Keep going. Okay, in terms of perspective, it looks like this. It's almost 14 million. It means then that the odds of you winning the lottery are 1 in 14 million because there's one winning combination in 14 million. So if you've ever heard things like your odds of being struck by lightning are greater than the lottery, that's actually quite true. Now, some people do win like lesser lotteries because sometimes if you have like say 5 out of 6 numbers right, they give you a smaller prize, or 4 out of 6 numbers right, they give you another prize. But if you actually want to win like the grand prize, it needs to be your odds are 1 in 14 million. Now, this is where gambling kind of comes in a little bit. I don't want to do a ton of gambling talk here, but this is what poker professionals basically do: is they look at their expected odds and they look at the payout. Okay, so for any of you guys who understand how gambling works, let's say that I told you that the odds of you winning were 1 in 2, 50-50 chance. Okay, And here's how the game's gonna work. If you win, I'll give you $10. But if I win, you give me 100. Would you play that game? Doesn't sound really good, right? But what happens if the scenario was something like this? Let's say that the odds of you winning were just like, say, 1 in 100, really low. And you had to wager $1. But let's say that you could win $500. Now maybe I'd play that game, right? Well, now if we apply that to the lotto right here, the way that our lotto system works in Canada is it's $2 a ticket. What is the minimum prize that the lottery should be for you to be even considering doing it? 28 million. If the lottery is not at least 28 million, it's not worth it. Do you get where I pulled that number from? If it's $2 a ticket, yeah, then the lottery needs to be at least that. Because in theory, here's what you could do. This is silly, but in theory, if the lottery was 28 million, I could buy 14 million combinations and buy every single one. Right? It would cost me 28 million because it's $2 a ticket, but I could cover every single one of those combos. And as long as the lottery was paying me 29 million, I'd make money. That's what poker players basically do. In their minds, they go, okay, so if I could do this, is this worth it in the long run? Well, okay, so here's where the problem is, though. The way the lottery system works, then, is what if two people happen to have the right numbers? They share the prize. So even though you'd be guaranteed to win, if they said the lottery was $30 million and you invested your 28 million hoping to earn the 2 million, what happens if I win because I know I'm going to win, I have to win, but she happens to get lucky? Well, then she gets 50 and I get 50 and now I've lost a whole bunch of money. So that's why it's actually a very poor strategy. But that's the whole idea of like expectant odds versus like the payout. If that makes sense. So if I give you a scenario that's the right odds, maybe you'd play it, right? But anyways, just wanted to show you the lottery here. I like this comic strip here. If you haven't read it already, here, that's what makes the lottery great. It's attacks people who can't do math. 4 lotto tickets, I'm guaranteed to win. It's like, no, you'd have 4 in 14 million jets as a winning. That's not that good, actually. Okay, let's move on. So here's basically a summary of what we've learned so far. There is the first formula right here, n over ABC, where A's, B's, and C's are how many identical objects you have. Right? This formula right here, we just divide by people who lose. This formula right here, we divide by winners and losers, because really you fall into one of two categories. Okay? So if I can kind of summarize here, it could be something where you don't have to divide by anything. Like, for example, we're all unique and special, so it's really divide by 1, 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 right? But it could be the kind of scenario where there's like a 1, 2, 3 ranking. So it would be all of us divide by 1, divide by 1, divide by 1, divide by 4, because the 4 losers all look the same. That's more or less what the second formula here does. The other possibility here, come on, keep working. The other possibility here is choose, where it's basically either you're on the winning side or you're on the losing side, right? And there's only 2 numbers on the bottom guaranteed. So, okay, now I want to show you another little twist that could come up here. It's actually possible that I could give you the answer to the question and you have to work backwards. So this is topical during like the NHL playoffs, right? Who just finished? Nashville and Anaheim, right? After they finish, everybody shakes hands, right? So what if I tell you that at the end of the thing, everybody shakes hands, and for some reason someone counts up there's 300 total handshakes. I don't know who counts them all, but okay. We shake hands, 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 we shake hands. Okay. I've shaken hands with everybody, right? Now she doesn't need to shake hands with me anymore because she already has, right? So she'd shake hands with you, and you, and you, and you, and you. And then now both of us are done. Now you'd shake hands there. Kind of see how this would work? It's more or less a choose scenario. When you shake hands, it's an unknown number of people, and when you shake hands, you need people to shake hands 2 at a time. An unknown number of people choose to shake hands with each other 2 at a time, and by the time you're done, there were 300 total. Now the reason why it's choose is that does it matter whether it's me shaking hands with Peter or Peter shaking hands with me? Does it really matter the order of how this? No, there's no order to a handshake, right? So that's why it's choose. So in theory, you could be asked a question like this, where something choose 2 is 300. Okay, but good news scenario here. There's only so many answers it can be. Now, it can't be 1.7, because it can't be a decimal number. It can't be -5. It can't be negative. It can't be 1, because it has to be bigger than 2, right? So now just grab your calculator, just start trying these one at a time. Try 15, choose 2. Try 20, choose 2, right? Guessing and checking will eventually get you there. $25? Okay, so guessing and checking gets me that 25 people picked 2 at a time get you to 300 handshakes. Okay, now in case, just in case, they throw the kind of question on there where they make you show somebody else's work, there is actually a way to do this algebraically. I would never ask you to do it this way because it's ridiculous, but it is possible for someone to show you your work. So here's another way of looking at it. What is the n choose 2 formula? How does it work? Well, it was supposed to be n factorial over n minus r, except we know r, and the r was 2, factorial, and then you also divide by the r itself factorial. So in theory, they could go right from here to there using the formula. Are you okay with that part so far? What does n factorial really mean, though? Well, n factorial is really n times by the number 1 lower than it, times by the number 2 lower than it, and you kind of just keep doing that for forever. Well, what does n minus 2 factorial mean? Well, it means start with n minus 2 and times by the number lower than that, by the number lower than that. But hang on, isn't this part right here, aren't all these things just going to cancel? Now, there still is a 2 factorial on the bottom, but if it's okay with you guys, I'm going to take 2 factorial, I'm going to times it up to the other side over here. So n factorial and n minus 2 factorial, they cancel. The n doesn't cancel. The n minus 1 doesn't cancel, but n minus 2 and onwards, they would cancel. So basically, you can turn this little bit right here into these two terms. Long story short, here's what you have. N bracket n minus 1 equals 600. Right, because 300 times 2 is 600. What kind of equation is this? Quadratic. So how do you solve a quadratic? That'll work, yeah. Make one side equal to 0. Make it n squared minus n minus 600 equal to 0, and then solve using the quadratic formula, or factor. This one I think factors, actually. I believe it ends up being n plus 24 and n minus 25. Which means that n is either negative 24 or positive 25. Now hang on a sec here. How can we have two possible answers? We can't have two answers. You can't have negative 24 people picking them 2 at a time. So it is possible that they might show you somebody's work for doing this. So the way that usually goes, just to recap here, is they would write it out in this sort of format here. Most of these things cancel here, like these guys right here cancel, leaving you just 2 things left over. You then times the 2 up to the side, by the way. Then you FOIL this out, bring it to the side, make it equal to 0, and you solve using a quadratic method. It gives you 2 answers, but one's extraneous. Don't do that. It's a waste of time. Right? Just guess and check. You know it has to be a whole number that's bigger, right? Just you'll eventually get there. Okay, let me do the last couple examples, and then I'll give you guys some time to work here. 5 swimmers, 3 make the team. What's the answer? There you go. 5 swimmers, but there's gold, silver, and bronze. Right. Just use that as a way to speed things up, right? Don't bother finding what the number is until you have to. Okay, gambling. Out of curiosity, any of you guys play poker? Play cards at all? okay, you know the basic concept of, aces beats kings and flush beats a straight kind of stuff. Know that sort of stuff. All right. Well, if you'd like to get into gambling, I'll show you way more. Let me show you some different things you can do with cards. I actually did this with my 30-2s. We actually played some poker and talked about probabilities. So yeah. Well, I mean, because it's math. So okay. Let's say you need to have a 5-card hand out of 52 cards, and you want them to all be black. Do you guys know how many black cards there are on the deck? Yeah. So the answer here is there's 26 black cards, and you need to choose 5 of them. There are a lot of all black hands. Now, I mean, that actually doesn't help you in poker because all black doesn't win you anything. But does that make sense? There's 26 black cards in the deck, and you need 5 of them. Why is it choose, not pick? Yeah, right? Like if someone says, what do you got? And I say, I've got an ace and an ace and a 3 and a 3 and an ace. If I take them and rearrange, it's the same thing, right? So order doesn't matter. Okay, so let's try this one right here. Oh, goodness. I'm going to have to grab my extension. A flush. How many, do you guys know what a flush is first? No, that's a straight. A flush is all of the same suit. Give me 1 second. Okay, flush. Do you guys know how many cards there are in each suit? There's 13, yeah. So if you want to flush, you need, out of the 13 cards in each suit, you would need 5 out of them. That makes sense? 13 cards in a suit, you need 5 out of them. However, this could be like, say, your flush in diamonds. But you could also get a flush in clubs. You could also get a flush in spades. Or you can also get a flush in hearts. Well, so it means if there's 13 diamonds in the deck and you want 5, you also could have won with 5 out of 13 clubs. You also could have won with 5 out of 13 spades, and you also could have won with 5 out of 13 hearts. Now, you can't have a flush in diamonds and clubs and spades and hearts all at the same time. So what should I be doing in between all these things here? Yeah, because you can have a diamonds flush, or you can have a clubs flush, or you can have spades or hearts. Here's a faster way of writing this, by the way. 4 times 15, choose 5. There's 4 suits. Oh goodness, that's not even close. 15, choose 5. There's 4 suits that you could win in. And in each of the suits, there's 13 cards, and you want 5 of them. That's how many ways there is to get a flush. Or you could just write it like this. Okay, now let's say you want to have specifically a flush of diamonds. How many ways is there to do that then? Just the 13 choose 5, right? Because you could just do the flush in diamonds, but you don't get the other flushes. So, okay, one of the best hands in the game, 4 aces. How many aces are there in the deck? How many do you need? All 4. What's 4 choose 4? Yeah, 4 choose 4 is 1 actually if you try it. Yeah. There's 4 of them. You need all 4, and order doesn't matter. So I mean, if I rearrange them, it's the same thing. But here's the funny thing about this though. You get a 5-card hand. Now, if you have 4 aces, it doesn't matter what your other card is. You could have the 2 or the 7 or the 9, but you still need another card, right? You still need to have a 5-card hand. So it's times 48 choose 1. Because there's 4 aces in the deck, you need all 4. There's 48 other cards left over. I don't care which one you have, but you need one of them. Does that logic make sense? Here's a full house. You want 3 kings and 2 queens. So let's try this. How many kings are there in the deck? Well, we want 3 of them. And we need 2 queens. How many queens are there in the deck? And we want 2 of them. Do I have a 5-card hand? Okay, so I can stop now. I don't need to times by like some extra little thing on the end here. So, anyways, in case you're wondering, if you ever watch like poker on TV, I mean, stuff like this is what poker players kind of are able to do in their heads quite quickly when they figure out, okay, how many flushes are possible? Okay, what are my odds? Okay, well, if I'm wagering $1, I better be earning back at least 7, otherwise it's not worth my while. I'll give you an example. Let's say that you watch the poker on TV and the thing says the guy has a 20% chance of winning. He's not going to win, right? But you know how sometimes they already have money in the pot? Let's say there's $1 million in the pot, and you had to wager 500 bucks. Now, I mean, to me, I don't really want to lose my 500 bucks, but 500 bucks to win $1 million, boy, that's a really good payout, right? Even if I only had a 20% chance in winning, that's actually a worthwhile risk because 1 in 5 times I'd win. I know I lose 4 out of 5 times, but I mean, imagine you played this game over and over and over again. The first time you lose, hey, you're at 500 bucks. The second time you lose, hey, you're at another 500 bucks. You're down 1,000. Third time you lose, you're out 1,500. Fourth time you lose, you're out 2,000. But hey, 1 in 5 times you're supposed to win, right? Let's say now you finally win. I know you're down 2,000, but now you won $1 million. Isn't that a game worth playing? Right? In the long run, right? One-offs and lucky streaks obviously cause problems, but that's what professional gamblers end up doing. So, all right. Anyways, let's move on. Okay, more examples. Pizza Parlor offers 25 different pizza toppings. How many different 4-topping pizzas are possible? Good. Why choose? Who cares what you put on first? Right? You have a cheese and pepperoni pizza, or you have a pepperoni and cheese pizza. It's the same pizza, right? So yeah, this would be a 25. Choose 4. Okay, we got 6 people who want to stand in a row for a photo. Is it a different photo though if we change around though? I guess you have to be really clear. This one said how many different arrangements can you have, right? And so if you had mom, dad, Phil, Jack, if you changed where they were, that would actually be different though, wouldn't it? 6 choose 6 is 1. There's more than one way that we could have you all rearrange yourselves. Right? 6 pick 6 works better. Because and this is what you guys are going to need to look for. If it gives something even a little subtle like this, as soon as it said different arrangements, that was the clue that order now matters. So now 6 pick 6, by the way, is the same thing as 6 factorial. Because really you have 6 and then 5 and then 4 and then 3. 6 pick 6 is the same thing as its factorial. 6 choose 6 is 1. 7 choose 7 is 1. A million choose a million is 1. But if you do pick, then it's its factorial. Do you guys know how blackjack works? You get 2 cards basically. And then you want them to add up to 21. It's 21 is blackjack. So how many cards are there in a deck? And you need 2 of them. Choose 2 though. Because does it really matter which one is which? Oh, how about this one? Julia wants to plant a whole bunch of trees. There's 10 trees that she's going to plant. 3 pine, 4 elm, 2 birch, and 1 willow. How many ways can she arrange all of her trees to be planted? Well, this one's a little bit different now because, hang on, how can I do 10 choose 3, choose 4, choose 2? Well, that makes it a little more challenging. Now, this is one that we've actually done before with the people who had to go do tasks at the school dance, if you guys got to that question on your assignment. Because really, there are 10 trees out there. 3 of them are pine trees, 4 of them are elm, 2 are birch, 1's a willow. Right? I don't actually, I mean, really, though, the 3 willows look the same as each other, right? If I wanted to write it like this, I could go pine, pine, elm, birch, willow, elm, elm, pine, birch. What am I missing? Elm. Right? If I were to change these 2 elms around, would you see a difference? Not really, right? So it's kind of like that letters sort of idea there, where you have 3 of one and 4 of another and 2 of one and 1 of the last one. Okay, 12 teams in a soccer league. Each team must play each other twice in a tournament. So you can see by the style of this question, this was an old diploma. Right? Again, they're not testing your ability to find the value. They're giving you 4 kind of scenarios down there. You got to figure out which one is which. So why don't you guys take a stab at it? I'll be telling you. 12 teams in a soccer league. Each team must play each other twice in a tournament. How many games will there be? There's no work to this, right? Okay, so first question you should ask yourself, does order matter? Why? It's just like the handshake question. If I'm shaking hands with Peter, or Peter's shaking hands with me, who cares? We're shaking hands with each other, right? If I play Jamie, or Jamie plays me, we're playing each other, right? So this is definitely a choose type scenario. How many people play a game at a time? Okay, so that's why it's all something choose 2. So 12 choose 2 makes sense. B or D then? Because they all play each other twice. This is what I need to help prep you for. It's hard, actually. I find it very frustrating because it's like, I don't know what they're going to ask. Let's try another one here. There's 10 people available to be on a committee of 6 people. How many committees can you form if Kristen and James have to be on the committee? Again, we're not asking you to find me the number. It's more just which of these scenarios fits best. 10 people are trying to make this team. 6 get to make it. But here's the twist. Kristen and James are already on the team. Everyday life scenario maybe you can relate to. You're trying out for, I don't know, rugby. A lot of you guys play. And you want to play for, I don't know, Team Alberta. But the coach of Team Alberta has a kid who's playing. And they're making the team. So if there were 10 spots available, there really weren't 10 spots available, right? There's really 9 spots available because you know that one of those kids is already a shoe-in. Does that make sense, the scenario? That's what's happening here. There's 10 spots, but there's not 10 spots. How many spots are really available? And how many people can actually make the team? Say choose 4. Why not pick? Why choose over pick? Yeah, you're either on or you're not. So there's the twist. This one's 8 choose 4. There's actually only 8 people vying for 4 spots because 2 of them are already on. You guys know these sorts of scenarios in everyday life, right? Like you can relate to them. Yeah. Okay. So you know that at the end of the day, there's like 3 spots left or something. Right? Yeah, exactly. Okay, another twist here. There's going to be some committees of 4 men and 5 women out of 10 men and 13 women. Well, one of the most common things people do here is they'd say, well, hang, there's 9 people right here vying for 23 spots. They might think, hey, it's one of the 23 and 9s. But that's really not how it works, because if it's the sort of committee where like certain roles have to be filled, where it's like, well, we have to have this many women and we have to have this many men, and this goes even further. There's a lot of places where, well, we have to have at least 1 African American person, we have to have 1 First Nations person, and we have to have 2 of these and 4. You get what I'm saying there, right? Well, then that really kind of limits down the pool. So the correct answer would have been A then. There are 10 men competing for 4 spots. There are 13 women competing for 5 spots. And we need to have the 5 men and the 4 men and the 5 women compete. Does that make sense? So it's actually not the 23 choose 9, because 23 choose 9 means that you could have a committee of all men. Right? I mean, that would be one of the possibilities, and this wants to try to prevent that. Okay. Research team of 6 people is going to be formed from 6 chemists, 8 politicians, 8 economists, and 15 biologists. But I'm going to give you a really weird stipulation here. I'm going to say that you have to have at least 5 chemists. Now, this 2-word little thing right here makes a huge difference. As soon as you see the word at least, it actually implies 2 scenarios. It means you could have 5 chemists, or you could have 6 chemists. You guys all get that there? If I say that you're going to have at least 5 chemists, it means that you could have 5 chemists, or you could have 6. So we actually have to do some adding math here. What we're going to have to do is find out how many ways is there to make a team that has 5 chemists and 1 other, or we could just do a team full of 6 chemists. No other possibilities are allowed, right? I can't have 3 chemists and 2 biologists and 1 politician because that doesn't meet my parameters. So how do I do this one here? Well, how many chemists are there? 10. I need 5 of them. Whereas in this scenario over here, there are 10 chemists and I need 6 of them. Now this is kind of like the poker question though. You know how when I did the 4 aces in the poker question, you still needed 1 more card. Well, it's kind of the same thing over here. You've got your 5 chemists, but it has to be a 6-person team. So you need 1 more person still. So how do I figure out that other person? Yeah. So how many are there? Well, there are 10 and 5 and 15 and 8, so that's 38. There's 38 total. Alright, so your 10 chemists have been picked, or out of the 10 chemists, 5 have been picked. So out of the 38, you're now down to 33. But it's actually not 33 choose 1. It's actually 28 choose 1. Because you can't pick another chemist. Right? You've picked, out of all the chemists that are available, you've picked 5. But now you can't pick another chemist, because if you picked another chemist, that would be the 6th chemist possibility. Right? So it has to be everybody but a chemist. You have to have, these guys are your chemists, and these have to be anybody, anyone but a chemist. So that's why it's 5, 8, and 15 adds up to 28. Now these 2 things are going to add to each other. What about these numbers right here, though? What will you do with those ones? Why? Somebody else. Yeah, you need 5 chemists and somebody who's not a chemist, or you just need straight up 6 chemists. That'll find you your answer. Hopefully that's one of the 4 answers now. What'd you get? Okay. Anybody else? Cool. Okay, here's an example, if you want to skip ahead, of one where if I was asking you to solve the question, I would just say guess and check. Like the question basically says, what choose 2 equals 10? And I would just say, well, just start trying it out. 3 choose 2, 4 choose 2, 5 choose 2, 6 choose 2, right? And you would just keep trying until something choose 2 equals 10. Right? But there is the chance they could have you show somebody's work and then do the whole find a mistake in it. It may just be easiest for me just to tell you where their mistake was right here. The n choose 2 formula is not n over n minus 2. It's n over n minus 2 with an extra 2 right there. Remember how choose means you have 2 numbers on the bottom? They actually made their mistake in step 1 right here. Everything else they would have done right. It's just they, I think what they did here is they brought this to their side, and then they said, hang on, n is actually n and n minus 1 and n minus 2. And they started like canceling all of the factorials that are the same as each other. Do you guys kind of get what I'm going with on this question here? So, okay. What else do I got left? Oh yeah, this one. I need to show you this one, because this one's challenging. Here I'm going to give you what's more or less a system of equations. You've got n choose r equals a number, and you've got n choose r equals 56, but you don't get to know either n or r. Now this would be really challenging because then you'd have to kind of guess and check 2 numbers. So here's how you'd solve this one. You'd say, well, hang on, n pick r really means n over n minus r factorial. That is 6720. That's the definition of what a pick is. Okay, well, that's a big number, right? Why is the choose one so much smaller? How does its formula work? Well, it's n over n minus r, but it has an extra r. See how when it divides by that extra r, it takes this number and makes it that much smaller? Here's what this really means then. 6720. If you were to take that number and divide it by that extra r factorial, it would get you down to 56. You see how that kind of works there? This number becomes smaller all because you divided by that last little bit. Well, now it's not so bad. Now we just need to figure out what r factorial needs to be. Now, you could guess and check from here, but I've got one more twist you can play, by the way. You could take 6720 and rearrange it to make it 67 over 20 equals over 56 equals r factorial, and flip these two guys around. So I'm like kind of changing the two denominators around. Who's got a calculator? What's 6720 divided by 56? Okay, so now you just got to figure out, well, what r value gives you 120? And now you just have to guess and check again, though. I think it's like 5 or 6 or something, probably. 5? Cool. So if they give you a question like this, they're really not testing your ability to do word problems, but you're probably going to be tested on your knowledge of these two formulas. Do you guys have your formula sheets with you, by the way? They're on the pink formula sheet I gave you. And it's very likely they're going to do some question somewhere on there that tests that you get how these two formulas work. So one of them is almost the exact same as the other, except there's an extra r factorial on the bottom of one. Oh, yeah, what else do I got here? Oh, here's the handshake question, by the way. This is on an old test. At a business meeting, everyone shakes each other's hand once. There's 91 handshakes in total. How many people were there? An unknown number of people are getting chosen 2 at a time to shake hands. And when you were done, there were 91 of them. Well, it's either 14, 15, 24, or 46. Skip ahead to this one right here. It's another like theoretical one. A choose 3 is the same as which of these? This one really was like a holy smokes, where'd that come from kind of question. A choose 3 is equivalent to which of the following? Well, I guess one thing you could do is you could just kind of start making up some numbers here. Let's just make up a number for A. Let's make it 10. 10 choose 3. Well, that means if you have 3 winners, how many losers do you have? I need to make it so that this number right here then, 10 choose 3, should be the same thing as 10 choose 7. So if A was 10, 3 minus 10, hang on a second, that doesn't even fit. 3 minus 10 will give you a negative number. It's this one right here. See, because if that was a 10 right there, that would be 10 minus 3, that would give you 7. You see how that works? If you're okay with the logic of 10 choose 3 is the same as 10 choose 7, 3 win, 7 lose, or 7 win, 3 lose, you get to go to the meeting. You have to go to the meeting. You don't have to, right? Like, however you want to choose it. So long as you recognize these ones are right here, then if that's a 10, then you just made up a number there. One last one, then I'll call our quits. The number of ways that 3 tiles can be pulled out of a bag of 20 is the same as how many tiles can be pulled out of 20. You're right. Yeah. Because really, this is 20, choose 3. 20 choose 3 is the same thing as 17, choose 20. Right? And essentially what I'm doing is I'm saying either pick 3 and leave 17, or pick 17 and leave 3. One last thought, then I'm done. You guys ever watch the game show Deal or No Deal? Right? They actually make light of the same sort of concept, because what Howie does is he makes you like pick one case, right? And then slowly but surely he makes you eliminate all the rest, right? But that's kind of the same concept you've got right here, where it's like you could either pick one and then not pick 19. What they're really doing to build suspense is that slowly but surely he just makes you go through all the ones that you don't pick. You know what I'm saying there? Like really, you just save a whole lot of time in that game if you just opened your briefcase right away and saw whether you won. But then there's no suspense, there's no game, there's no mechanism to it, right? But you get the same kind of concept. You could either pick one briefcase and not pick 19, or you could pick 19 briefcases and the one you don't pick is then yours. It's kind of the same math either way. The way they do it though, then that whole banker thing, getting you to leave your briefcase, there's a lot of math to that too. Okay, I'm done. I've taught you pretty much everything you need to know in this section now. I've covered most of like the twists and the tricks and stuff like that. What I need now to do, I need to give you guys time. So Thursday and Friday are work time, and then Monday we'll try our first quiz. Sound good? So try to get that first assignment done. Okay. And if you need to ask me for help, do that. So I kind of expect that. So you got about 20 minutes today, and then you've got 2.5 hours between tomorrow and the next day. It should be a decent amount of time to work on it. Sound good? We have one lesson. We're done, guys. One last lesson.